Theory that we have been discussing previously is called the classical theory. We are now moving to the modern theory of partial differential equations, which took place a little bit more than 100 years ago. At least it started then. Here are some major mathematicians who have contributed to the modern theory. Sobolev, Poincaré, Hilbert. There are many other great mathematicians who have done very big efforts in this field. Let us just recall some important aspects of linear algebra before we continue. What is a vector space? A vector space has the property that it's a set, and its members are called vectors. We can call, if we have two arbitrary vectors x and y, and we add these vectors, which has some meaning, we get another vector which is also a member of this vector space. Moreover, if we have some constant, real constant, and we multiply this constant with some arbitrary vector x, we obtain a new vector, that is a new element in this vector space V. So that's the definition of a vector space. Moreover, we have something called a scalar product, inner product if you like. It's some operation which has the property that x star, we can call this scalar product for star, x star y is a number, real number, with the following property. We will go through this very fast since you should know this from linear algebra. If we have some vector x, we have this linear property that k1 multiplied with some vector w1 plus k2 multiplied with double w2. This is a vector, and taking the scalar product with some other vector x, we obtain this identity. So the scalar product is linear in the second variable. And it's also linear in the first variable due to the following fact, that we assume that the scalar product is symmetric. Moreover, if we take the scalar product of one arbitrary vector x with the vector itself, we get a positive number. And this is strictly positive if x is different from 0. So the only case when this product can be 0, x multiplied with x is 0, is when x itself is 0. What is an inner product space? Well, it's just a vector space where we have defined a scalar product, or inner product star, if you like. And the norm of this vector is defined in the following way. This is also very basic knowledge in linear algebra. So let us just take some very simple example of vector spaces, for example R2. If x is a member of R2, then x is a vector of this form. And if we have a vector y, which has two real component y1 and y2, this has two real components as well, x1 and x2, then the scalar product in R2 the usual scalar product is defined in this way. We just take the first element multiplied with the first element here and add the product of this element with this element. So in the case of this usual scalar product in R1, we often write this dot instead of this star. And the norm in R2 is defined in this way. This is just the square root of the x1 square plus x2 square. What does it mean that we have some convergence? Let me just add that, of course, if we have n elements of this vector, that is when x is a member of Rn, then we get the obvious extension of this rule. We will come back to this later. Convergence of elements. If xn converges to some vector x when n goes to infinity, then we have this property satisfied, that the norm of the difference between xn and x turns to 0 when n goes to infinity. Let us take an example of this. If, for example, xn is a member of R2, a two-dimensional vector, and xn is defined in this way, where n is some positive integer, for example, then this element will be a little bit larger than 1, and this element will be a little larger than 0. When n goes to 0, then this element will converge to 1, and this element will converge to 0. So we can, it's natural for us to guess that we have this convergence, that xn converges to this element converges to this element in this space R2. But we have to prove it. And recall the definition of convergence here. We have that xn minus x in norm should converge to 0. So what is this norm? Well, we just put the difference between xn and x. That is, the difference between two vectors are just this element minus this element. That first element of xn minus x, and the second element is this element minus this element. And we know the norm then must be this number square plus this number square and the root of this number. So it's easy for us to see that this will be the square root of 2 over n square, and the root of n square is of course n, so this will be the root of 2 over n, and of course this turns to 0 when n goes to infinity. So in this way we have proven that this element converges to this element. So in a vector space or an inner product space, we say that we have a convergence when the norm this norm turns to 0. And here we have an example of this. Let's turn to some definition. A vector space or an inner product space, capital V, is complete if any vector sequence of vectors xn which converges to x has the property that x also is a member of V. So if we just take some example, if V is equal to the elements of all rational numbers called capital Q, that rational numbers are the functions which are on the form a over b, then this space is not complete with respect to the norm given by this. The norm of x, which is in R1 equal to the square root of x square. Note that this is the norm in R1. And why is that not a complete space? Well, if we take, for example, x equal to the square root of 2, it's 1.4142. So if, for example, now take x1 equal to 1, the first number here, x2 equal to 14 over 10, which is 1.4. x2 is equal to 141 over 100, and we get these three numbers, 1.41. x3 equal to 14 over 1000, then we get 1.414, and so on. We just let the sequence look like this, and you know we construct the sequence in a way such that xn will converge to x, which is the number square root of 2. Then we note that the square root of 2 is not a rational number. So in this case we have an example where we have rational numbers which converge to some element x, but this element is not a member of the space Q of rational numbers. So this is an example of a space which is not complete. Note the following. If V is a m-dimensional vector space, or in the inner product space, and m is a finite number, that means that that we have m basis vectors, and recall what a basis vector is. A basis vector, a set of basis vectors spans the space. So that means that any vector w in V can be written in the following form, where ai is an element of R. We can show, it's possible to show that such a space is complete. That's not trivial to show, but it's possible. So in order for a vector space to not be complete, it must be infinitely dimensional. Let us also consider the following definition. Vector space capital V is which is an inner product space. Inner product space is called a Hilbert space if it's complete with respect to the norm induced by the inner product. And Hilbert is one of these persons. You have him here. He was is not the inventor of the space, but he used it and is known for making the most remarkable results in the modern theory of partial differential equations.